Thank you so much. Thank you so much. First of all, I thank Angela and Emil for inviting me to this seminar. It's a great pleasure for me to visit KTH. Again, I was here 5 years ago, I think. So I am working on multi-agent systems indeed, and actually this topic, method of averaging inequalities, was motivated by two applications, and I will start with one motivating application, which deals with, which is concerned with distributed algorithms to intersect convex sets. Such algorithms are also referred as constraint or optimal consensus algorithms. So I know that I think that more or less everyone knows what usual consensus algorithm is. What is constrained consensus algorithm probably is it's a bit less known. So I will start with this application. Then I will tell the core of averaging inequalities theory, and then we return to that first application. Then also I show how they can be applied, those inequalities, to opinion dynamics models. So that's the plan of my talk. Okay, let's start with the motivation. So as a motivation, I mentioned one classical problem of applied mathematics, problem of convex sets intersections. So if you imagine convex sets in three-dimensional space, you realize that it's very difficult to visualize. So what will be the intersection of those three planes, for instance, or those three ellipsoids? In two-dimensional space, it's much easier to visualize, but if I ask you to write the, by the way, can everyone see that red pointer on the screen? Okay, great. If I ask you to write the equation on this intersection, it's difficult. So let's try to solve the simpler problem. Instead of describing the whole intersection, let's find at least one point. And we assume that such a point always exists, so the intersection is not empty. Why this strange problem is interesting? Actually, well, in fact, we often meet such a problem in our life. So it has plenty of applications in numerical analysis, optimization, data science, and so on. I mentioned just few applications. So actually, in our school days, we were solving linear equations, or as mathematicians would say, we were intersecting hyperplanes, right? So as soon as your system of equations becomes large scale, cool methods like Gauss method of variable elimination, right? They're not very efficient. So for instance, if you want to compute page rank or SGR rank, right? Or solve large-scale Leontief balance equations in economics, you probably need special numerical methods. But it's also a very special case of convex set intersection problems. And another example, which is very well known, I guess, to people who work on data science or machine learning, is a linear classifier problem. Right, so I show actually the planar picture, two-dimensional picture. So we are interested to find a hyperplane, which in our situation is just a line, right? That separates two clouds of points. Say that green hyperplane is nice, right? Because all the black points are on the left, on white ones are on the right. This red is also nice, that green is not nice, right? So because most of points are on the same side, both black and white. If you think what is a hyperplane, so if you try to find the equation of a hyperplane, right, so the coefficients of the linear equations, you will realize that actually this problem reduces to the solution of inequalities, right, system of inequalities. And again, you can consider each inequality as a convex set, right, in the space. And you again need to find point X, which is now the set of coefficients of your hyperplane, such that the system of inequalities holds. And there are plenty of other problems. So there is a great survey by Combet. I think his name should be pronounced in this way. The foundations of set theoretic estimation. So there are problems of intersecting strips, ellipsoids, and some other nonlinear convex sets, let's say so. Actually, there are methods, well-known methods in mathematics, how it works. So to introduce those methods, it's convenient to use projection operator. So I think you know that, okay, let's consider finite dimensional space. It works in fact in Hilbert space. But let's consider classical Euclidean space of finite dimension. You know that if I take a convex closed set, right, for each point X, I can find the nearest point, right, in my set omega. And the mapping, which takes X and computes this projection, is called the projection operator. So there are some nice properties of that operator. For instance, it is known that such an angle is obtuse, right, or obtuse. So the following inequality holds. Okay, and for instance, for a hyperplane, the projection operator is very easy to find. So there are methods like method of alternating projections or POX, projection onto convex sets, which I illustrated for two sets, but it works for an arbitrary number of closed sets. So you take initial point x1, you first project it to the first set, you get something called a y1, then you project it to the second set and get x2, which is your first approximation. Then you perform the same operation with x2, you first project to first set, you find y2, and you project back to the second set. You get x2, and so on. So you have a sequence of those points, x1, x2, x3, and it can be proved under some natural assumptions that they converge. Of course, you need the existence of intersection. There is a slightly different method, so you can project to both sets and then compute average point, and it also converges to a point in the intersection. And in reality, such algorithms are very, very old. So they date back to 1930s. It works for Neumann and some Italian works, work by Kaczmarz, published in the Proceedings of Polish Academy of Sciences. Many of such algorithms have been rediscovered, reopened in relation to perceptron learning, for instance. Then there were publications in Russian and Soviet literature, Bregman's work, Gubin, Polak, Reich's work, Yakubovich work on recursive object inequalities. But that's those old works actually are not what we are interested in. We are interested in distributed versions of such an algorithm. And actually there are such distributed versions. So in those algorithms, we have several agents. Each agent actually keeps some closed convex set, so it's the constraint, some constraint in the space of all decision variables. So there is one agent with his constraint, another agent with his constraint, and so on. And agents actually are interested, again, to find a point in the intersection. Those agents may be not interested in exchanging information about their constraints, right? So those constraint sets could be kept private. For instance, well, if you are negotiating, I don't know, about salary, so you probably have some minimal salary in your mind, right? Well, minimal if you are a candidate, or maximal if you are employer, right? But you don't want to disclose it, for instance, during the interview. So there can be some economic, financial interest of agents concerned related to those sets. Okay, long story short, we have agents, we have individual sets, and it's supposed, of course, that agent knows something about his constraint set. At least agent can compute the projection. And there are several algorithms. Actually, there are at least 3 known algorithms in discrete time. And there is Kalli's algorithm in continuous time. They are similar to consensus algorithms. So they also involve stochastic weight matrix, as usual, the Groth model or consensus algorithm, but they also contain those nonlinear operators. So actually, you may ask why that second algorithm, in fact, it was initially proposed to solve linear equations, why it performs double projection. So agents first compute the projection, then exchange those projections, compute averages, and then project again. So actually, well, first of all, as Stephen Morse explained me, this provides much faster convergence, but again, there can be some privacy issues because, for instance, here, agent need not even disclose its state, right, to the other agent. So agents exchange only the results of projection, right? So it's projection state. So algorithms are similar, yet slightly different. And actually, it is known that they work under some natural assumptions. I will show some assumptions later. But okay, why do they work? So if you open relevant papers, you will see that the analysis is pretty different from what we basically do for averaging algorithms, right? So normal consensus algorithms. So solutions are bounded here, but actually the usual Lyapunov function, which is the diameter, right, of the convex hull spanned by the agent sets, it does not work here. So such a diameter actually need not decrease. And in fact, there is another sort of Lyapunov functions usually employed in such a problem. So like a distance to the desired set. Right, actually, and desired set, okay, so desired set is denoted C star, so it's an intersection of all constraints. And the set of equilibria is narrower than unusual consensus algorithms. Actually, it is this set. So such actually vectors that components of all agents are equal and belong to that desired set. And in fact, conditions for consensus, understood in this sense, are also different. So connectivity restrictions actually are different from classical consensus algorithms. So typically, you need something like strong connectivity instead of spanning tree existence. But actually, why do those algorithms work? So let's consider this first algorithm, for instance. I claim that actually those algorithms work for 2 reasons. The first reason, of course, is the special structure of projection map, which is in fact a paracontraction. So paracontraction is a weaker form of contracting map. Contracting map is a map which maps to arbitrary points into other points such that distance between the images is strictly less than distance between the initial point. So here, the condition is a bit less restrictive. So first of all, we allow the mapping to have fixed points, right? So the distance between fixed points, of course, remains same. But on the other hand, if you take a point which is not fixed and another point which is fixed, then the distance between the images, well, image of a fixed point is a point itself, right? The distance between the images still strictly less than the distance between initial points. So first reason actually why the algorithm really converges is this paracontraction property. So actually those algorithms perfectly work if you replace the projection map by general paracontraction. And the second observation, which actually naturally leads to an averaging inequality, to what I call averaging inequality, is the following. So let's take an arbitrary point in this desired set. And okay, it should be norm actually, same symbol as here. And consider the distance from the state of agent I at time k to the spot. If you look carefully at that algorithm, you will realize that this distance, which we denote xi, it of course must be negative, right? Because it's a norm, it's a distance. It is easy to show that xi at the next time step, k plus 1, is not greater. So the proof is written here. I am not going to actually pronounce it aloud. And the slides, I guess, will be available after the seminar. So that distance is not greater than the following average. The following average. So it looks like a consensus algorithm, but instead of equation, you have inequality. So I claim that the algorithm, in fact, converges because of two things. So paracontraction map, actually PI, and this hidden system of one-sided inequality. And actually, this is how those inequalities look like if you write them in the vector form. So when I write the inequality for vectors, I mean actual element-wise comparison. So this would be a normal consensus algorithm. And this is, it's another mathematical object, strange mathematical object, which is inequality. You can consider same as the same actually construction in continuous time. There is no principal difference, but I will consider mainly discrete time case. So those inequalities, in principle, may be considered from two viewpoints. So you can say, okay, but it's a special case of what we call recurrent or differential inclusion. Right? So inequality, well, you can say that it's, in fact, the relation like that. So xk plus 1 belongs to something, belongs to this function plus negative code, right? But, well, inclusion will be with unbounded right-hand side. On the other hand, you can consider this as a perturbed consensus algorithm, right? So you can say, okay, so I have unknown disturbance here, which, however, is sign preserved, so it's always non-positive. However, actually, those considerations do not help much. So actually, from them, it is not very clear what can be derived for such inequalities, right? So it seems that, okay, the best thing you can do is to get the upper estimate of x of k, or x of t here. In fact, you can derive much more. And it's a sort of surprising property of such inequalities. So let's first consider some general notation symbols. So let's consider our system of inequality. It is easy to show that the maximum of maximal element of vector x, which is a solution to inequality, does not increase. So it's same as in consensus. For minimal element, this is of course not correct, right? We don't have any information what happens with minimum, because actually minimum in principle can go to minus infinity if your solution is unbounded. But basically, we are interested in solutions that have an a priori lower bound, like in the previous example. So our vector x of t, it was positive by construction, not negative by construction, because it's a vector of distances. Notice that general solution to such an inequality, of course, can behave very regularly. So if you consider the trivial example with, say, two agents, you can construct a solution which oscillates. So actually, you can take x1 of k, like -1 to k, and here you can take some random element from this set 0 plus -1. So, and if you fix x2 of k at sufficiently large constant, these two inequalities hold. So generally speaking, inequalities actually admit very irregular solution. But paradoxically, if your graph is connected enough, for instance, W is constant, and its graph is strongly connected, solutions of such inequalities do converge to consensus. And this really surprising, because this inequality seems to lose constraint of vector x to in principle proves anything. Well, actually, this notation you probably know. So if you have a matrix W, you can associate a graph to that matrix. There are a lot of arguments, actually, a lot of quarrels how to direct arcs in this graph. So in graph theory, as usual, arc from I to j corresponds to positive entry wij. But on the other hand, if you look on those inequalities or consensus protocols, actually this positive element corresponds to influence of j on I. But okay, let's re-enter arcs as shown here. So from I to j, arc from I to j corresponds to entry wij. Well, there is such a concept as cut in the graph, so it will occur at one place. Cut is just splitting of all nodes, division of all nodes in the graph into disjoint sets, non-empty sets. Well, and that's a mathematical result. Sorry, there will be some mathematics actually that part of the talk. So that part is pretty technical. So actually, let W be a constant row stochastic reducible matrix with positive diagonal. So it appears that in such a situation, irreducible means that its graph is strongly connected. It appears that each solution to the system of recurrent inequalities, which we had on the previous slide, this system, converges to consensus. So converges to a vector of identical components. Of course, it is possible that all elements go to -infinity, so that's a sort of degenerate situation. But we are primarily interested in bounded solutions. If your solution is bounded, then it appears that at infinity, your inequality transforms into equation. In the sense that the difference between right-hand side and left-hand side vanishes asymptotically. So first of all, inequality, not an equation, but inequality, implies consensus. And second, actually, this difference, which I call residual, converges to zero if your solution is bound. Well, actually, the same, of course, holds for inverted inequalities, right? So greater or equal is the only difference that here vector can go to plus infinity. And well, if your graph has isolated, strongly connected components, then such an inequality decomposes into several independent inequalities, and it guarantees not consensus but class. It can be shown, in fact, that this consensus condition is also necessary. Unlike normal consensus algorithm with equation, actually here strong connectivity is necessary for consensus. Okay, and very simplified sketch of the proof. So in the case of static matrices, you're still connected?
Yeah.
Okay, so the sketch of the proof of the following. So let's introduce the ordering permutation of the vector. So let's order the elements of our vector x in the decreasing descending order, right? So the first is maximum, then second largest, and so on. The last is minimum. Okay, so matrix is constant, and remember that we assumed it's diagonal to be positive. So let's introduce the following quantity Q. It's a minimum of all positive entries. The particular diagonal is not less than Q. Okay. So let me take the stylus maybe and write it here. So particular diagonal is okay. Then let's make the following observation. So the maximum is not increasing, right? I already mentioned it. It's not increasing, so it converges to somewhere. If it converges to minus infinity, there is nothing to prove, right? So if maximum goes to minus infinity, all other elements also go there. So only the case where this C star is finite. Another observation. If you have arc in the graph from I to j, so positive entry in the matrix, then it can be easily shown that the following inequality. Why? Because look at this inequality, right, for element I. In the right-hand side, you certainly have xjk multiplied by this weight. And you have some other element, right, elements corresponding to non-zero entries. Everything except for xj certainly is not greater than this maximum. So you can prove that inequality. For the same reason, recalling that wii greater than 0 and hence not less than q, you have similar inequality where instead of j you have I, right? So each node is connected in the network is connected to itself. So you can prove the following inequality because again here you have xi with its weight wii which is not less than q, and all the other elements are not greater than maximum. And from here, in fact, I claim that the following inequality can be derived. So remember that y2 is the second largest element. Actually, we will explain why it follows in a few seconds, but notice first that if you have such an inequality, and we know that q is positive, right? Then we automatically have that y2 should go to the same limit as y1. Because, well, the left-hand side goes to the limit, right? This term goes to 1 minus q to that limit. And so the limit of y to k is not less than c star. But y2 does not exceed y1. So it means that its limit is same, actually, as for y. But why this inequality holds? Well, maximal element should correspond to some index, right? So y1 corresponds to some index I1, for instance. Remember that our graph is strongly connected. So from I1, you should have at least one arc. to other nodes, right? Otherwise, you have no strong connectivity. So there should be J different from I1, so that I1 is connected to J. And applying the first inequality, you have estimate for X by I1, right? Why have Y2K here? Because J is different from I1, right? I1 corresponded to maximal element. J is different from it. And hence, Xj cannot be greater than second largest. Also, if you have any other element M, which is different from I1, I can use that second inequality and check that Xm also not greater than what is written here, right? Because, actually, M, here you have M, right? Actually, Xm, but M again is different from I1. I1 corresponds to maximal element, so Xm does not exceed the second maximum. And look what we have. We have found actually some quantity, right, which is written here. Actually, we have found some quantity which is written here, which is not less than all elements of vector xk plus 1. Right? So it's not less than xi1 at time k plus 1, but it also not less than all other elements of vector. That exactly means that y1, so maximum of all elements, does not exceed what is written in the right hand side. And actually iterating the procedure, you can derive similar inequality. So I'm not going to bother you with that because one proof is already too much. But you can derive it similarly. Similar procedure allows to get such an inequality. What does it mean? It means that that vector y goes to a limit, the limit c star. Right? So using the mathematical induction, you can prove that all elements of vector y go to c star. But y is just a reordered vector x. Okay. So surprisingly, inequality implies consensus. Inequality is a very, very, very loose, right? Very loose restriction of the vector, the first ones. But in reality, not. Well, actually, I have not proved that actually there was residual convergence, but okay. And there are extensions, so I briefly mentioned. So, of course, you can extend it to some classes of non-constant matrices. For instance, you can consider reciprocity conditions. So one of them is the following. So if there is such a cut in the graph, that at some period k, group I influenced group J, right, which is its complement. So there is some agent from I who decided to influence agent from J. Then, in no less than L steps, there will be response from J to I, right? So there will be influence. It will not be immediate response. It can occur in a finite number of steps. So L is some constant here. And it appears that under our assumptions, like positive diagonal here and actually uniform positivity of non-zero elements, more or less same result will prove. So again, you have consensus and, Here actually the situation is more general. So we don't assume the connectivity. So it appears that every solution converges, first of all. And moreover, if two agents persistently interact, right? So this means that, okay, so they interact infinitely many times under that assumptions. Actually, there is consensus. So in each strong component of the persistent graph, actually there will be consensus. And for bounded solutions, this residual goes to zero. reciprocity actually is not so seldom, occurs not so seldom. In fact, the graph with isolated, strongly connected components is reciprocal, right? So if your matrix is static and the graph has isolated, strongly connected components, actually repeatedly strongly connected matrix, in fact, is also reciprocal. So repeated strong connectivity is also a special case of that reciprocity. Type symmetric matrix, and in fact, for this situation, you can even relax the condition of strict positivity of your weights. So they are all examples of reciprocity. But okay, it was a technical part, right? So actually, long story short, inequalities, in fact, magically entail consensus. Okay, and now let's return to our applications. So I think I have 10 minutes or so. Okay. Normally supposed to be 1 hour, right? Or
50 minutes, I think. But,
okay, let's return to our example, which we had on that slide. So actually, as I already promised you, we can put here arbitrary paracontractive operators. So instead of projections, you can consider paracontractions. So whose actually sets of fixed points Ci, and actually we assume, as previous, that intersection of those sets is not empty. So such an algorithm, in fact, it was first noticed by Fulmer, Liu, and Morse. Such an algorithm allows to find a common fixed point of paracontractions. So actually, you can solve not systems of linear, but fact systems of complicated non-linear equations, complicated non-linear matrix. I will show the example on the next slide. And actually, using the observation I already showed you, you transform, you derive a system of inequalities, averaging inequalities, right, for this vector of distances. And actually, you know that bounded solutions of inequalities actually have finite limits, and the residual will asymptotically vanish. And if we omit some details, this means basically that the difference between this pi and its argument vanishes asymptotically. So I will not prove this rigorously, it's some argument, but boundedness plus paracontraction allows to prove it. And if you actually denote this deviation by epsilon k, you have what? You have normal consensus algorithms plus something going to zero, the right-hand side. And actually, using actually one of Kayle's result on robustness of consensus, you can prove actually that those agents actually reach consensus. So the deviations components go to zero, which in fact allows to prove that all of them go to C star. In fact, you can prove that actually vectors Ci converge. This is also done actually in our view, but it's not so important for now. This is just a sketch of the proof why it works. So as I promised, let me show you an example of a paracontracting operator, which is not projection. So actually, the following mapping can be shown to be a paracontraction if Fi is strongly convex, and this alpha is small enough. So actually, such mapping appears to be paracontraction. And in fact, you can consider the following problem of simultaneous optimization. So assume that each agent keeps function Fi. Then you know for some magic reason there exists a point where all of them simultaneously attain the minimal value, the minimal values. Then our algorithms applied for such maps actually looks like that, and it computes the optimal. But of course, it's very strange optimization problem. In reality, optimization problems are different. So the simplest optimization algorithm, for instance, proposed by Nedic in her paper, like that. So agents have their constraints, and the functional is a sort of sum of cost functions belonging to the agents. And the algorithm, in fact, looks similar to what we call constraint consensus, but still it's a bit different. So I believe that the method of recurrent inequalities can be extended to cope with such problems. And this VI of CI seems to be a natural candidate for the solution of inequality. But in reality, we will not get exactly the inequality we need. So there will be something in the right-hand side. So I'm not going to show that, but this is a sort of ongoing research. So how to combine inequalities with distributed optimization, true distributed optimization. And okay, so I briefly would like to mention another application which also leads to inequalities. So let's consider first what actually I call Altafini's model in quotes. Actually, so Angela knows that model a lot, right? You love it. While in quotes, first of all, Professor Altafini considered continuous time dynamics. And second, he dislikes the term Altafini's model. Actually, I am not going to tell you much about that model, but actually it is similar to consensus algorithm with the only difference that this matrix is not stochastic. So modules in each row sum to 1, but the elements entries can be negative, which corresponds to some negative relations like distrust, competition of agents, and so on, enmity, and so on. And okay, so elements of X are called here opinions, those Aij called influence weights, and well, so their signs can be plus or minus. The classical model occurs when there are no negative elements, right? And it is known that in many situations, opinions demonstrate the following interesting properties. So they reach almost consensus. So it's not consensus, but it's consensus in absolute value. So if you forget about signs, actually limits will be same. Why does this happen? For exactly the same reason. This algorithm contains an inequality inside. And it's much simpler to derive it than in the case of constraint consensus. It suffices to consider the vector of absolute values. So this is not a norm, this is an element-wise module. And if you perform this operation, you will realize that such a vector obeys the following inequality. So this is again not a norm, it's a matrix of moduli, right? And this is a stochastic matrix now multiplied by the vector at time t. So it's again the inequality. And actually playing with our result, you can prove that, okay, so under natural conditions, like for instance, strict positivity of non-zero elements, reciprocity, strong persistent interaction graph, you have consensus of moduli, you have vanishing residuals, and moreover, if your consensus is non-trivial, so actually opinions do not vanish, do not converge to zero, in fact, you can prove that the graph starting from some time step should be structurally balanced. The structural balance actually means that enemy of an enemy is a friend, roughly speaking. Or more precisely, when we speak with directed graph, we should be more precise. You can divide all agents into two groups. such that influence weight between members of the same group is non-negative, and influence weight between members of different groups is non-positive. And actually, inverse statement is also true. So if starting from some k, and notice that this division into two hostile camps does not depend on k, right? So actually, for large k, actually, it's dictated by the sign of the vector. Inverse statement is also true. If this strong form of structural balance takes place, then you have non-trivial consensus in modules. And the last example, so here I will not tell you much. This is a Hexelman-Krause model, but not a standard model, but a model with additional constant term here. This is a so-called Hexelman-Krause model with truth seekers. Roughly speaking, it's supposed that some agents, so they are interested to find some value, let's say state of the world, right? So which is called truth, and they actually they educate themselves, they read books, so they invest some time to find the truth, and for that reason, at each step of the opinion iteration, they become closer to that value. And the stronger this attraction, actually, the faster normally, right? The agent should approach the truth. And here, as in the usual Hexelman-Krause model, you have what is called bounded confidence. So opinions of agents that are very distant from your opinions, are ignored, right? So you're not interested in the opinions that are far from you. So tau is what is called the truth, as I told you. Lambda is some desire to know the truth, right? So how fast you are attracted to it. So here we have a weight matrix, which is state dependent. State cannot be found explicitly. So it's a very complicated system. And unlike classical consensus algorithm, you have that constant term here, which creates a lot of problems. But again, you can prove convergence of the model because this Hexelman-Krause system contains an averaging inequality. So if you introduce the distance to the truth, you again see our inequalities. Well, now matrix depends on the state, but it doesn't really matter because we still have reciprocity relation, at least in the situation where all confidence ranges are equal. And actually, we can prove that all solutions converge. For instance, actually, two agents either converge to same value if in the same connectivity component of the persistent graph, or their opinions are distant, actually, from each other. At least the distance is not less than the confidence value. And moreover, agents who really want to know the truth, they really find it. So their opinion converges. Well, you can say, okay, but it's a natural result, it's just bounded confidence model. With this constant term, in fact, the averaging inequalities gives, I would say, the only elementary proof, which I can tell to students, for instance, to engineering students. Because the original proof given by Bernard Chazelle in his paper used extremely non-trivial tools from complex analysis. So what he called S-energy. It's a method of power series, in fact. And actually, there is one more alternative proof, which was actually incrementally built on several papers published in different years, but it's also very complicated. So the method of inequalities allows to prove the theorem in less than one page. And that's the literature which I cited. So my own papers and some other references I cited. Thank you so much. for your attention. I just mentioned the conclusions actually, but they are long, so I just show them. So we discussed a new tool, which is averaging inequality, which extends the theory of consensus. There are extensions to communication delays and so on. There is the only drawback, I would say. They do not admit Lyapunov analysis. It's difficult to say anything about convergence rate. And actually, that's the problem. But to advocate the inequalities, I would say that convergence of consensus algorithms with time invariant matrices is also far from being well studied. So only some conservative estimates are used. And as I mentioned, the application of this distributed optimization is a topic of ongoing research and higher order methods as well. So thank you again for your attention.